In our previous examples, we assumed that the roots obtained from the characteristic equation were distinct. Okay, when we say distinct, it means no repeated of any of those roots. What if some of the roots are repeated? Then we need to do a slight changes to the general solution. So suppose the root r, so we are concentrating on one root, is repeated m times. So it is repeated m times. Then what you have to do? Then you multiply or you raise r raised to power n, and then you multiply it by a polynomial. Now this polynomial will have n in terms of n, and each term will be multiplied by a constant. If it is repeated m times, then this polynomial will be of degree m minus 1. So you start from c1 plus c2 multiplied by n plus c3 raised to square until you go to the last power, which is equal to m minus 1. As an example, suppose we have this example now. So if I want to find what will be the general solution for these roots, and we assume that these roots are obtained after we converted the recurrence relation into characteristic polynomial, and we made it equal to 0 and found the roots. And what if we found the roots? Then how to find the general solution for this recurrence relation? So these are the roots, and if you notice that we have these roots repeated 4 times, these roots repeated 4 times, 3 times, twice, and once. So what will be the general solution? Here I'm assuming that the name of the recurrence relation is an. So we will have an. Now, since 1 is repeated 4 times, this is how we are going to find the answer. So it will be multiplied by a polynomial c1 plus c2n plus c3n squared. And we continue because it should be of degree 3. So we should continue for the next one, which is a plus c4n raised to power 3 multiplied by 1 raised to power n plus. Now minus 2 is repeated 3 times. So we are using c1, c2, c3, c4. So we need to start with the new constant variables. So it will be c5 plus c6n, and this is degree, so repeated 3 times. So we go up to degree 2. And this is multiplied by minus 2 raised to power n. Plus, now 3 is repeated twice. So it will be C8 plus C9 multiplied by n, 3 raised to power n. And finally, we have C10 multiplied by minus 4 raised to power n. Or what we do if we don't want to multiply the root by the polynomial, if we want to just distribute the root over the polynomial directly, and there is no need to know how many times the root is repeated, we can do the following. Now you can just, below every root, you say that this will be n raised to power 0, this will be raised 1, and this is 2, and this is 3. So for this root, the first constant will be multiplied by n raised to power 0, which is 1, and multiplied by 1 raised to power n, which is 1, plus c2n plus c3n squared plus c4n raised to power 3. And we can do the same for minus 2. This will be n raised to power 0, which is 1, n raised to power 1, and n raised to power 2. So the answer will be plus c5 minus 2 raised to power n plus c5 multiplied by n minus 2 raised to power n plus c6 n squared multiplied by minus 2 raised to power n. And next, this one also will be n raised to power 0, which is equal to 1, and this is n. So the answer will be plus C7 multiplied by 3 raised to power n plus C8n multiplied by 3 raised to power n, and finally for the last one, which is minus 4, it will be, I think I am missing one, so 3n, so C1, C2, C3, C5, here it should be 6, so I am missing one here. This should be 6, and this should be 7, and this should be 8, and this should be 9. So for this will be C6, this will be 7, and this will be 8, and this will be 9, and finally for the last one it will be C10 multiplied by minus 4 raised to power n. And this will give us the constant multiplied by a variable and multiplied by the root in all the terms. As an example, try to find the general solution for the following recurrence relation with the following roots. So we have 1 repeated twice, we have minus 1 repeated 3 times, and we have 2 repeated 4 times. So if you want to find the general solution, first you have to label those roots with the polynomial that you are going to multiply with each repeated root. So for the first one, here the polynomial that you will multiply for this repeated root will be 1 because n raised to power 0, and here next one is n. Now for the next one, it is repeated 3 times, so we have 1, and we have n, and we have n square. And for the last one, I'll use a different color. For the last one, this will be 1, this will be n, this will be n square, and this will be n raised to power 3. And as you notice that the power is increasing starting from 0. So what is the general solution? The general solution that you have to multiply each root by a constant and raise it to power n. So the first one, it will be C1 multiplied by 1 multiplied by 1 raised to power n plus C2 multiplied by n. Because 1 raised to power n is 1, and we multiply the first one by 1, and we multiply the second one by n. Now if we go for the next one, it will be plus, since this is minus 1, so the first one will be C3 multiplied by minus 1 raised to power n plus C4 multiplied by n by minus 1 raised to power n plus C5 multiplied by n square multiplied by minus 1 raised to power n. This is for minus 1. And now for 2, it will be C6 multiplied by 1 multiplied by 2 raised to power n plus C7n 2 to the power n, C8n square 2 to the power n, and last we have C9n to the power 3 multiplied by 2 to the power n.